Hello everyone and welcome to our latest PV Tech Talk Product Series webinar. This is Mark Osborne, Senior News Editor at PV Tech and the moderator for this webinar. Today's title is Eliminating Catastrophic PV Tracker System Damage Due to Extreme Wind Conditions, which will explain key aspects of a technical collaboration between PV tracker firm Soltech and specialist engineering consultancy firm RWDI. Now, this has resulted in Soltech's DI wind analysis tool to enable correctly designed utility-scale PV power plants that plan deploying tracker systems in the new era of large area PV panels, and especially mitigate the impact on systems vulnerable to high wind loads. We have two guest speakers sharing the floor today, Bernd Zwingmann, structural engineer at Soltech, and Matthew Brown, project manager and principal at RWDI. So a quick reminder that we will have time for a short Q&A session after the presentation, and so feel free to post questions throughout this webinar. We also have staff from both the companies online to help answer any questions you may have. Okay, so we have a lot of great info to get on with. So if both presenters are ready, Bernd, the floor is yours.
Yeah, thank you, Mark, for the kind introduction, and welcome to the audience. My name is Bernd Zwingmann. As Mark already said, I'm a structural engineer at Soltech. In case you don't know Soltech, here's some general figures. Soltech is one of the top 3 PV single-axis tracker suppliers in the world and the #1 in Latin America, with an installed power of approximately 10 gigawatts worldwide. This presentation will focus on the Darwin method that Soltech uses for tracker design. Using the Darwin method allows Soltech to obtain wind loads that include all wind effects like dynamic pressure, dynamic amplification, and stability. The method has been developed together with RWDI, today represented by Matthew Brown. The experience has shown that building codes do not well predict wind loads for PV tracker design. Already the static coefficients for a tracker are not the same ones as for a monoslope roof, which are provided by the code. Also, the code does not provide dynamic amplification of the wind load depending on the activated mode shapes. And most important, there's a lack of information regarding wind-introduced tracker instability that can happen for eigenfrequencies of approximately 1 Hertz and even beyond. That is why a better wind load prediction method is essential. Darwin can predict wind loads on the flexible tracker structure, taking into account its geometric and dynamic properties like length, cross-sections of the members, stiffness, mass, inertia, and so on, which can change from project to project. The obtained wind load includes a dynamic part that increases the static wind load due to resonance effects and instability. Soltech's tracker field is based on typically 3 different tracker types. You can see the example layout on the right side. The interior tracker has a big share in the field and is usually very competitive. The exterior tracker and the edge trackers are stronger, and they protect the interior tracker, especially when the tracker field is positioned in high tilt angles. The wind load Soltech gets from Darwin do not only depend on the position of each tracker inside the field, but also depend on the different dynamic properties of each tracker type. This allows a very specific design of each tracker type. Now I would like to hand over to Matthew to explain how the Darwin method works.
Thank you, Bernd. So when we talk about single axis trackers and wind loads, there are several components that we need to consider. And I don't know if you get a little uneasy with equations. I do, so this is the only equation I'm going to show. We have several components. So we have inertial loads, represented on the first term on the left-hand side of this equation. We have the stiffness, which is the what the structure needs to resist. We have damping forces, and then on the right side we have two applied forces. We have the buffeting, which represents the wind buffeting, so the applied force of the wind onto the structure. And then we have the self-excited forces in the case of a flexible structure, and we call these aeroelastic forces. So moving on, we can see what are the different dynamic effects that affect single axis trackers on the next slide. So we have several mechanisms. First, we have what we call resonant vibration. And resonant vibration, there's two causes of this. The first is just general wind buffeting, so the applied forces of the wind onto the structure can cause resonance. But we also have what we call wake resonant effect, which is caused by wind shedding from upwind rows in a tracker field. And you can see that on the upper right figure, that there's increased turbulence from upwind rows. Now, there are two other mechanisms that we call torsional instabilities, and there's two types generally. The first type is what we call flutter, and this is characteristic of high tilt angles. And the other mechanism is what we call torsional galloping, sometimes also referred to as torsional divergence. And this is really characteristic of low tilt angles. And on the image on the lower right here, you can see that these torsional instabilities cause the rotations at the free ends of the tracker, and they can become very divergent and excessive. So what is this hybrid method? So the components on the next slide, we can see there are several components of the die wind, and this is effectively a hybrid method. And the first component are rigid pressure model tests. So we get some data from those, so we'll talk about that. We also have sectional aeroelastic model tests, and we obtain different data from those tests, which we'll talk about. And both of those kinds of tests provide inputs to numerical simulations. And these components put together provide a very flexible design approach for Soltech. And the first component on the next slide are rigid pressure models. And there's two main pieces of information that we obtain from this type of testing. First of all, we get static wind load coefficients. And the static wind load coefficients represent a rigid model that is assumed to be infinitely rigid. So it's not flexible at all. And it's so stiff that you can't have any dynamic effects. Now, we know most structures aren't like that, and so we can also obtain approximations to the inertial forces we talked about earlier using what are called dynamic amplification factors. And these approximate the inertial effects and can be combined with the static to get an estimation of the total wind loads acting on the trackers. Now, there's one big assumption in this approach, and that's that the displacements are quite small, and they do not include fluid structure interaction or what we call aeroelastic effects. Now, on the next slide, we can see the second main component of the die wind approach, and that's a form of an aeroelastic test called a sectional model test. And essentially what this does is it takes a short section of the tracker, which is nominally rigid, and we mount it in the wind tunnel on a spring suspension rig on both sides of the section, as you can see in this video. And that allows the rigid section to move aeroelastically. So it can rotate, and if it need be, it can translate up and down and side to side. And there's really one real key piece of information that we extract from this type of test, and we call those aerodynamic derivatives. And these derivatives describe how the total damping and the total stiffness of the system changes with wind speed. And due to the aerodynamics, damping can either increase or decrease, and stiffness, represented by the natural frequency, can also increase and decrease. And these derivatives provide one of the key inputs, along with the pressure data, into two numerical methods. And the first is what we call a Flutter analysis method, or FAM. And this predicts when the total damping in the system crosses zero, so really the critical wind speed of an instability, and a buffeting analysis method, which predicts the response of the tracker. So whether it's torques or rotations, this is the method where we really can predict the design wind responses for design. Now, on the next slide, I want to talk about a bit about the components of the die wind. Now, the components of the die wind are not new. What is new and innovative of die wind is the combination of the components. And I just wanted to highlight some of the roots in the flutter and buffeting analysis within wind engineering. And it goes back a long ways. So the flutter analysis goes back actually to the mid-30s with the work of Theodorson. And that work got adopted into wind engineering by Robert Scanlon in the 1960s. And this really was motivated by the Tacoma Narrows bridge failure shown in this video. And this is a form of flutter. So this was really the driving force for the beginnings of wind engineering and long span bridges. And then the buffeting methodology that we use today was started in its infancy in the 1960s and continued into the 1970s. And long span bridges rely heavily on the buffeting technique to produce design wind loads. But one thing that is important is this buffeting technique has been validated against physical aeroelastic model testing over and over again. Now, the first numerical analysis is what we call the FAM, or the Flutter analysis method. And what this does is it predicts where the tracker becomes unstable due to wind. And this can predict whether it's torsional flutter at higher wind or higher tilt angles, or torsional galloping at lower tilt angles, can predict where the total damping crosses zero. And it's important to note that this is a mathematical definition of an instability. So it's not linked directly to a rotation or a torque, but it's where the total damping crosses zero in terms of the onset, the critical wind speed of an instability. And with that, I'll pass it back to Bernd.
Yeah, thank you, Matthew. So we can take these results from the FAM method, from the flood analysis method, and plot them into a graph for different tilt angles, and of course for specific tracker type. And this curve shows at which wind speed the tracker, with its specific properties like position, field, stiffness, damping, length, and so on, gets unstable. In the diagram, we can also mark the site-specific design wind speed to distinguish between the stable and the unstable zone. In this example, you can see that the tracker for this tracker is stable at 0 degree. However, for small changes in the tilt angle, for example, by only 5 degrees, it becomes already unstable, or it gets to the limit of the unstable zone. And we can also see that the tracker is generally stable for high tilt angle, like 45 degrees and beyond. In this case, for example, this tracker would be positioned at a high tilt angle, for example, 50 degree, to be stable during a storm. Then there's the second method, the so-called buffeting analysis method. And this is much more interesting than the FAM, because it's not only a theoretical prediction of the instability, but it describes the behavior of the tracker in the wind. because being in the stable zone is not necessary, but it's not sufficient for a reliable design. The tracker can fail without being unstable. And one interesting part of the Darwin method is that it can predict the dynamic load when the tracker is close to the instability limit. So the buffeting analysis method provides twist angle and the corresponding wind loads for the tracker moving in the wind. On the right side, you can see two graphs. So the upper graph is a tracker response where the tracker gets unstable because the amplitude is increasing with time. And on the lower graph, you see a stable response because the amplitude of the deflection is decreasing with time. This is an animation from RWDI where you can see how such a structural response could look like. When you focus on the arrows, you can see that they grow bigger and smaller. And they actually represent the wind load that is acting on the PV panels. And due to this wind load, the tracker starts to move in the wind. And this is a realistic movement that one would expect in the modeled storm event that you can show here, that you can see here. So how can we use this method now for the design? This slide shows this. On the right side, you can see a typical diagram that we get from the Darwin method. On the vertical axis, there's the torque moment coefficient, and on the horizontal axis, the reduced frequency. F is the first torsional eigenfrequency, L is the chord length, and V is the design wind speed. On the left side of the vertical dotted line, the design is not feasible because all trackers with these properties would be unstable. The horizontal dashed line is the static moment coefficient that does not depend on the reduced frequency. That's why it's a constant value. And the continuous line is the dynamic moment coefficient that increases the closer the tracker design gets to the instability limit. If you pick a tracker design with its corresponding reduced frequency, the torque tube needs to resist the moment resulting from the sum of both coefficients, the static and the dynamic one. Here you can see an example of the effect of the dynamic coefficient. The torque tube, the torque moment of a specific tracker increases here with the wind speed. For high wind speeds, the dynamic component of the moment becomes significantly higher than the static part. This increase can be predicted by the BEM method, but not by only using dynamic amplification factors. Recently, RWDI finished a series of full 3D aeroelastic tests to verify the Darwin method. And Matthew, could you please introduce this work?
Yes, thank you, Bernd. And as Bernd just mentioned, Soltech has also undertaken full 3D aeroelastic model testing with RWDI. And if we think back to the animation that Bernd showed from the buffeting analysis of the 7 rows, and each row moving in reaction to the wind, so that represents effectively a numerical representation of a 3D aeroelastic type model, and we can do that in the wind tunnel. So effectively, what this type of testing does is it takes the full scale structure with its mass and its stiffness and its damping, and obviously its geometry, and it shrinks it down to model scale. And so in this photograph, you can see one of the scenarios that we investigated with 17 rows in the array, which is a lot in terms of a full aeroelastic model. And this allows us to look at, we can change the tilt angles, we can change the wind directions, but really the thrust of this research was to validate the previous buffeting predictions that Soltech's been using. And so we can see on the next slide a comparison of one of those cases for a low tilt angle. So this graph is presenting torque on the vertical axis, and on the horizontal axis is the reduced frequency, similar to what Bern had described before. The red vertical line represents the instability limit as determined by the Flutter analysis, so the FAM part of die wind. And then we have two sets of results plotted. One is from the buffeting analysis, so the BAM prediction, which is the set of blue curves. And then we have the full aeroelastic model results, which are the green set of curves. And there's three curves for each data set. There's the mean plotted with the circles, and then on either side of the mean are the peak maximum and the peak minimum. And as you can see, the trends line up extremely well as they approach the instability threshold, and the results agree quite well. So that's the response. And on the next slide, we can look a little closer at the critical wind speeds at these lower tilt angles. And this is really important to understand. So when we talked about the Flutter analysis predictions, so the FAM, we talked about defining the instability at the point where the total damping crosses zero. So that's a mathematical definition, but it's not linked directly to a rotation or a torque level. But when we go into the wind tunnel with a 3D aeroelastic model, we can't easily obtain that exact point of where the damping crosses zero. So we need to rely on measurements of typically rotations. And when we do that, we need to pick a threshold. So we pick a threshold, and where the response crosses that threshold defines the onset wind speed. And so we went back and with the buffeting, used that type of definition, so a threshold of rotation, similar to what we used in the 3D aeroelastic model. So you can see this on the right-hand plot. We have wind speed on the vertical, and we have tilt angle on the horizontal. And the dashed line represents the Flutter predictions, and then the solid line represents the 3D aeroelastic results, and the square dots represent the solid line represents the buffeting prediction, and the square dots represent the 3D aeroelastic. And the buffeting and the 3D aeroelastic align quite well. And as you can see, the Flutter gives generally higher prediction, and that's due to just the difference in the definition of the onset wind speed. So with that, I'll give it back to Bern to wrap up.
Yeah, thank you, Matthew. As a summary of this presentation, I want to point out that Soltech is investing a lot of effort in wind tunnel testing and also the development of design method when it comes to wind load. And this is beyond the requirements of building codes. It's much more detailed. And yeah, based on the results, the trackers, based on the results we get from those methods, the trackers use a high tilt stow angle position to mitigate the risk of instability. The flexibility of the Darwin method allows Soltech to provide a specific tracker design for each client and each project. Thank you for your attention.
Well, thank you both, Bernd and Matthew, for what was an excellent presentation. Thank you so much. Before we start the Q&A, I just had a couple of things just to remind people that when the webinar slides actually disappear after the Q&A session, the actual webinar platform is still live. So we have Soltech and RWDI staff available to answer more questions. So there's no rush to exit the platform when the actual webinar slides disappear. That's obviously to help you guys, because it's a very complex and technical session here, so don't feel afraid. Also, please note, sorry, but Zachary has had to go. He was on a very tight, Matthew was on a very tight schedule, and we have Zachary Taylor, Senior Engineer and Associate Principal at RWDI, to actually handle the questions for you. Now, let's actually start with a question for Zachary and RWDI. You showed several animations. One of them was the actual tracker in a Flutter condition. Just to be sure, this was still a model. It wasn't actually like a real scaled version of in the wind tunnel that gave those effects.
Yeah, so this is Zach here. The animation that you're referring to, I think, is the one with the pressures applied. And so in that case, we exaggerated some of the rotation. So that's a buffeting response. So that could be below the stability limit, as Bern discussed. That could be just, these are flexible systems, and in a turbulent wind, you can see a lot of motion. And so it's important to understand the loads associated with that motion so that you can design accordingly.
Okay, great. Thank you for that. One for Bernd. I think you did actually mention this, but maybe just a good point to just go over it again. The question is really asking, does Soltech stow at low tilt or at high tilt when we're dealing with this new knowledge and the trackers?
So in general, what you can see from this analysis, so in general you can stow at any tilt angle you want, firstly, so that's up to the designer. You just need to know that if you choose flat positions, it's more difficult to get the tracker stable, so you need to put more stiffness in it. You can do it by using several drives, for example. There are such solutions in the market. The Soltech tracker has one single drive in the middle, the one that is usually used, the SF7 system. And this tracker has a stow position for high tilt angle. I think I also said it in the conclusion. So it depends a bit on the side and so on, but it's typically between 45 and 55 degrees what we choose as a stow angle.
Okay. Related to that, from a stow angle point of view, there's another question here. It says, does this tend to increase the steel weight of rails, beams, and piles in the structures if you're having it at that angle?
You cannot generally say something like this. That's too easy. What is true is, of course, that when you put a wall in the wind, the wind is pushing much more on the wall than if you put a roof in the wind, yeah, like a carport roof. And the wall of a carport is totally different. But if you imagine that you are inside the carport with no walls, you are not very well protected. But if you are behind the wall, you are very well protected. So you could say that if you stow all trackers in flat positions, the interiors are not so well protected. But but the loads are generally for the outer row, the loads are smaller. But when you stow them in a very high tilt angle, the outer rows get very high loads, but the inner runs are much more protected. So it's not so easy to give a general answer on this.
Okay, that's good. I think there's a group of questions, and maybe both of you may want to contribute to this. Obviously, we're dealing with larger area modules. They are heavier, so there's lots of questions sort of related to like, have you measured things like wind pressure loads on these large area modules, especially in a 2P position, a 2P platform? So
yeah, maybe I can give a short answer, and maybe Zach as well. So in general, this method is, so what we presented now is like general description of the method. Of course, we can analyze any kind of width and length and so on. It's just additional effort, to say so. So we have a couple of configurations that are covered by this method, but of course, when you come up with a very strange type of module, then you need to do some additional analysis just to be sure that that you cover these properties. But the method itself doesn't have a limit. Just the numbers, to say so, that are in it for now. But we don't stop. So this is not a history overview. So this is what is ongoing now. So we go on developing further this method. Matthew showed the aeroelastic testing to back up the method and get some additional results on twists and so on. So that's a living method, to say so. So it will always progress forward. So if we find that we need new conditions to be tested, then we just include it into the scope.
And I can add a little bit to what Bernd said there in his response. As you can imagine, full 3D aeroelastic testing is quite expensive and complicated. And one of the advantages of the Daiwind approach is to get a deeper understanding of the aerodynamics. And so while module sizes are changing, while other factors are changing, there's a great amount of flexibility in the approach because of how well understood the aerodynamics are in terms of damping and stiffness, that we can provide some insight on different module sizes, different other factors that might go into the decision making. And then once we're getting kind of converging on an answer, then we go in and do a full aeroelastic study to confirm all that analytical work.
Understood. Thank you, Zachary. Another one here for you, Bernd. I think questions really asking about, and I guess this is in connection to the larger modules. But is there a typical distance between rows that reduces the buffeting turbulence, for instance? And I'd like to add in perhaps that what are the design considerations for a PV power plant, especially when we're talking about bifacial modules and their orientation, how that plays a part in how you analyze the risks associated with high wind.
So in general, we always do project-specific solutions. I think you understand that what I said before in the high tilt stow position. Of course, it's more beneficial to put the tracker rows closer together. So the closer you put them together, the better the protection for the interior ones. Of course, there's a certain limit, so you can't put them like with 1 meter distance. Doesn't make sense, but you can put them closer together and you get some better conditions. In case of bifacial modules, it's more complicated, because when you get too close, then the additional yield that you get from the ground reflection decreases. So typically for bifacial projects, we would choose a bigger distance between the rows, but this also depends on the location and on the ratio between direct and indirect radiation. So in fact, that's a more detailed study which is needed to combine the advantages and disadvantages of having more yield from the bifacial, but maybe paying a bit more for the steel structure due to a wider row spacing. So that's also nothing that you can just generally say for all projects. It's always project specific choice.
Okay. I think just to confirm, because there was again, there's a group of questions. I'm looking at the time as well, so this probably will have to be the last question that you can answer. But when you look at, because I think this is something novel for people that are coming on board here about, you do take all of this analysis into consideration when designing a plant. But I think there was you showed in one of your slides there, Bernd, that the outer, the outer rows would be strong, inferring that they would be stronger, and that would also be analysed regardless of the size of the modules. And again, people are talking about inferring the larger the larger modules that we now have. And I guess it's just a question of, how is that designed in? Do you have to do that every time, or is there specific standard things that you've learned from that you could just automatically introduce? I think there's a couple of questions in there, but it's really people going in and around that topic.
Yeah, that's a good thing maybe about the Darwin method. So everything is numerically available. So we have several commercial software joined together for a numerical process, to say so. So we can more or less, not totally, but more or less automatically design tracker fields, defining a list of input variables, which is quite fast. But we can also, so this would be what you say, like a general answer. So I have a list of project-specific parameters, put them into a calculation tool, and then I will get a certain tracker field. But this would be more generic. And then, of course, there's also the possibility to look at each corner of the plant, of the solar field individually, especially when the field is not, not all fields are rectangle, right? So there are a lot of very strange shapes. So in these cases, it makes sense to manually look carefully what to design there.
Yeah, thank you for that, Bernd. Yes, there is. I think there's a lot of sort of other questions here. They're very specific to very sort of probably unique challenges some people are obviously facing, and the whole idea here is that you can cater for that kind of thing in advance. And I think this is something that people I think are trying to get to grips with. But we really have run out of time. We've pushed the envelope a little bit further than we should do. But I thought the questions were really good. And so thank you, Bernd. Thank you, Matthew, who's gone. But Zachary, thanks for filling in at short notice. And thanks for everyone for watching. The webinar will appear. The presentation will go on YouTube. We'll announce it to everybody that registered. And you'll be able to have the presentation as well as watch the webinar again, because certainly I'm going to be watching it, especially some of the software analysis and how the trackers perform is very incredible stuff. So thank you all for attending, and that's the end of the webinar. Thank you. Bye-bye.